So last time I'd asked you guys to work on these multiple choice questions from AP Classroom or whatever. I noticed this morning when I went to look, a lot of us didn't do it or hadn't done it. So I reset the stuff so that you could keep going, right? Like I show 6 people haven't done anything. So if you hadn't done that yet, please kind of take care of that for Thursday. We'll talk about the questions on Thursday. But if you haven't done the 11 multiple choice questions through the MyAP site, please do that before next class. Again, if you went to go do that this morning and are like, I'm locked out, I reset the due date, so you should be able to go back and do them if you forgot about it and didn't do it yet. So pretty pleased with sugar on top. Please try to get to that here before next class. Okay. Next up, questions from 2-3. Does anyone still have stuff from 2-3? We finished up 2-3 last time, so there's still a couple dangling. Katie.
62.
62. Sure. All right. What did you try? Or what was your instinct when you looked at this, even if you didn't try anything?
I was really just not feeling this one. I wasn't excited.
Okay. So I would say when I look at this one here, what it most closely reminds me of is one like 25, or 27 or 29. And what did we end up having to do to solve one like this? Multiplied by the conjugate, right? Let's do the same thing here with 62. But which conjugate? Top or bottom? Both! Let's do both conjugates.
Wait, so if you have a radical on the bottom, would you have to multiply by both conjugates then?
Well, it's because they're both like radicals, right? And if I try direct substituting this, I get 0 over 0, right? So you could try them one at a time, but doesn't you do one first or the other first? You want to do them both. However, Katie, the way I'm going to multiply this, I'm not going to multiply all 3 of these things together. I'm just going to multiply the conjugate pairs together to start.
Do you have to do plus 1?
Oh, yes, thank you. Those should be plus 1s. Thank you. All right, so when I multiply the root x minus 6 minus 2 times root x minus 6 plus 2's, I get x minus 6 minus 4. And then I just get that other piece that I'm not going to multiply in yet. And then here I'm going to multiply the conjugate pairs on the bottom. So when I do that, I get 3 minus x minus 1. And then root x minus 6 plus 2. Everybody so far so good? Let's simplify. What is 6 minus x minus 4 simplify to? Sure, I'm going to write as 2 minus x though. Same difference. How about the 3 minus x minus 1? those will reduce, and guess what's even the best part by reducing those? Why was I getting 0 over 0? Because of that x minus, or 2 minus x factor in the numerator denominator. It just canceled out. So I'm at a point where I can like do my direct substitution now. Now keep in mind, I'm not really direct substituting, right? I'm like using limit laws to do this because, right, this isn't a polynomial, so I can't really direct substitute in it yet. But this is like, I'm really, technically I'm doing this. But we won't have to do this for much longer before we get more power for our direct substitutions. Yes.
Wait, so, but I thought it's like if it was like a radical function, can you just like do substitution or?
I think the rule was that you can do it for a rational or a polynomial, but not radicals. Let me go find. That's okay. No, these are important questions. Yeah, polynomial or rational.
Okay, got it. I'm sorry.
No. You don't have to apologize. These are good things. All right. So there's that. Now, I made this look really easy, right? And you're like, I looked at this and grinded on this for like 20 minutes and didn't feel like I made any headway at all. When you know what to do, they are easy. You have no intuition, though, as to what to do, right? That's part of why I assign some of the harder homework problems, is to make you sit down and think about it, like, so that we learn, like, what should I be looking for? What doesn't really work? What if I tried and just didn't really help, right? Like, it's part of getting better at this is to everybody, when they're doing it the first time, rides the struggle bus eventually. And then you get off this, once you get to, you see what to do, it's like, yeah. And then when the next time you run into something similar, you're like, I have an idea. What if I do both conjugates? And then don't multiply it all together. If you did that, you would have gotten into a mess and not been able to go forward. Even if you did try both conjugates, you had to go, okay, what if I just do it the smart way where the multiplication's easy and then see what I get? Stop and look around. Like, we live in a world of smartphones. Everybody has GPS. Nobody like tries to get somewhere by, okay, I'm just going to try drive in the right direction and like have to stop and look around. I try to figure out where I'm at, right? We all know exactly where we're going until we get to do something like this. I'm like, we don't know where to go. You have to stop and look around a little bit. Others from 2-3. Chanel?
Number 59.
Sure. So this is like a super, like, I like this because this is like a real analysis problem. Now it's an easier version of something, but this is like something you talk about in like a real analysis course. That's like your theoretical calculus course. If you are, I'm a engineering person, or I'm going to take like a lot of math courses, eventually you run into this. It's like the theoretical background for like how calculus works. Hi. How are you?
I'm good. It's for someone.
Okay, I'll give it to someone. Christian Lazera. Come on down. You gotta. This feels like raffle tickets. I know, because I got the same envelope in the mail and I was just as excited as you were. All right. So this is a piecewise function, right? That's what this looks like. Now it's weird because the pieces are when x is rational and when x is irrational. Okay. Let's think about this. Is this continuous? Is this function continuous? Does it have any discontinuities in it? It sure better does. Yeah, how many discontinuities are in this guy? Infinitely many. right? Everywhere where the function switches from rational to irrational, which is kind of at every point, like in between, okay, so it's like you have infinitely many discontinuities here. Like one thing you'd learn in a real analysis course is between any two rational numbers is infinitely many other infinitely many rationals, right? But if you think about comparing like rationals to irrationals, which one do you think there's more of? There's more irrationals. Is there a lot more or a little more? There's a lot more irrationals than rational. It's very quickly becomes really weird to think about, right? How in the heck are we going to take the limit of this thing that's like got infinitely many discontinuities? I don't know that I can do a left hand and right hand limit to it. Like, what do I do with this? What tool do we have that we can use to take a limit that doesn't depend on the function that we're actually trying to take the limit of? Squeeze theorem! Yes, that's exactly what we'd want to do on this. So, we need to come up with a function that'll lower bound f of x and upper bound f of x. Yes?
But so we're not choosing squeeze theorem because there's like discontinuities in between these two functions. Is that why the x
well, there's infinitely many discontinuities in this. So even at 0, like, are the points bounding 0? Right? Bounding x equals 0? Is it attached to 0 or is it not attached? I don't even know, right? Like, what kind of number is right next to 0? Is it rational or is it irrational? I don't even know the answer. I couldn't even say. Like, so you can't even like try to draw a graph and like make a reason like, okay, so it's like behaving like x squared going into 0, or, you don't even know. So that's why we're trying to do a squeeze theorem here, because it doesn't depend on f of x anymore.
Okay.
So what function would be a lower bound to f of x, regardless of whether we're talking the x being rational or irrational? 0, yeah. 0 will work. Right? Because x squared is always going to be greater than or equal to 0. And 0 is always 0. So this would be less than or equal to everything. What's going to be a good upper bound for f of x? What? X squared. Remember, we need two things that are going to have the same limit, right? So if I pick like -1 instead of 0 and like positive infinity instead of x squared, when I do the limit of both sides, I won't be able to say anything because they don't have the same limit, right? Right now, think about this for a minute. X squared is always greater than or equal to x squared, right? And because x squared is always positive, or I should say non-negative, could be 0, but that's going to be greater than or equal to 0 also, right? Everybody agree? Okay, so now all I need to do is take the limit of 0, which is
0.
Yep, 0. Limit of a constant is a constant. And take the limit as x approaches 0 of x squared, which is 0. How do I do that?
Plug it in.
Direct substitution. And since these two limits are equal, we can say by the squeeze theorem, the limit as x approaches 0 of f of x is equal to 0. Done. Now, this was tricky because you had to think to yourself to pull out the squeeze theorem to use, although that shouldn't have been too long to get there, considering you only have like 2 ways to evaluate a limit right now. It's like direct substitution. Well, that's not going to work here because we don't have continuity. It's not polynomial or rational, the thing that we're trying to plug into. So I can't do that. Okay, well then maybe I could graph it. I don't know how to graph this. You have infinitely many discontinuities in it. That's not going to work. All I'm left with is squeeze theorem. Yes, Shana.
Wait, so you can't use direct substitution because only one of them is a polynomial?
Well, this is a piecewise function,
Oh, okay.
right? Not a polynomial function.
Okay.
Even if it was two polynomial pieces, you still couldn't use direct substitution necessarily.
So piecewise function is like there's two parts to it?
Mhm.
Like, okay.
Or more.
Okay.
You know, like you could have like the bracket, you can have like 26 things.
Okay.
It's terrible, but like still piecewise, right? It doesn't matter how many things you have.
Okay.
Everybody's, does it feel okay?
Yes, thank you.
And again, like Mr. Kulik, that took like no time at all. Well, first you had to realize you need to use the squeeze theorem. Not trivial to do that, right?
Yeah.
Then you had to cook up upper and lower bounds whose limits were the same thing. Not trivial to do that. This was really the only choice, 0 and x squared. You had to pick those two. I don't think there was anything else you could have used. So it's, you know, I guess you could have done negative x squared and positive x squared. That probably still would have been fine. But anyways, whatever. Like, you had to get the bounds, which was not easy. You know. All right. The limits were easy once you had the bounds, and you knew that you had to do the squeeze theorem. That part was easy. Who's next? Anybody else? Giselle. Yeah, sure.
No, I just couldn't go with that, but
Yep, no problem. All right, so we have this. Can I do this direct substitution on this? No, because I don't know what f of x is, right? So it's not rational because I don't know what f of x is. Can I do my, like, the quotient law for limits and put that limit on the numerator and denominator? No, because the bottom limit goes to 0, right? So what do I do with this? This is the trick. I'm going to multiply both sides by like an x minus 1. Now notice when I do this that this limit is kind of attached to this x minus 1, right? So when I multiply it to the other side, it comes with it. So if I do limit laws on the left, I can write that as the limit of f of x minus the limit of 8. And on the right, this limit is now the limit of a polynomial. That I can do direct substitution on. The limit of 8 is just 8. 10 times 0 is 0, and then I just add the 8 over. There we are. There's my limit. This was the tricky part, right? Once you made that realization of like, okay, that's how I have to get that thing over to the other side, is the limit has to come with it. Everything is kind of algebra from there. Not too bad. Seeing that first step is the tricky piece. You're welcome. And I guess here, if you want to really think about it, what we did is we kind of did this, and then we used like our limit law to stick it all into the same thing. Right? So we kind of did that. If you want to think about it that way, that's a little bit clearer as to what I did. Chanel?
So I did cross multiplication. Is it a coincidence I got it right, or
I mean, so here's the thing. I think you kind of got a little bit lucky, because if you go and you look what you would have really kind of done there is, in doing cross multiplication, you did this limit law, but the denominator is, that limit is 0, so you shouldn't do that.
Okay.
That's, now it worked out okay this time. I think we kind of got a little bit lucky in that regard.
Okay.
But in general, you doing the cross multiplication is kind of, you're invoking this limit law
Okay.
when we shouldn't be able to use it, because the limit of the denominator is 0.
So wait, so how is it like making this limit law happen? Is it because like,
How, okay, what is, help me out here. You used the personal pronoun. I wasn't really sure what is it?
when you're using cross multiplication,
Uh-huh.
how is it invoking this this law?
Well, because this is like inside of a parenthesis. So you can't cross multiply with this because there's no denominator technically. That's all like one thing.
Okay.
For you to cross multiply, you had to push the limit here so that you can do this, so that there is a fraction outside of the parenthesis,
Oh, I understand.
right?
Okay.
So it'd be like, if you had like square root of x over y equals 10, you can't cross multiply with that because the fraction is inside of the square root.
Yeah, you'd have to square.
If you think about, if you did it this way, then you can cross multiply because now the square root is, the fraction is outside of the square root.
Okay.
What we're saying is this, you couldn't, that limit law you shouldn't have been able to do.
Okay.
Is that, you see what,
Yes.
okay.
Yes.
And again, these like little nitpicky algebra questions are really good ones. Like, I want to talk about this stuff, so don't feel like, oh my God, I keep asking all these questions. They're really specific only to me. No. This is the good stuff. Like, it is in the detail. Like, the details are important. Like, if we need to like really grind down so we see why I could use or not use something, that's important. Okay, that's a good use of our time. Okay. All right. Okay. Anybody else? I think these were the worst of the ends here. Okay. You okay? Okay. I'm asking you, Giselle, because you had said something on Friday about.
I watched videos online.
Okay.
So
And you feel much better?
Yeah.
Okay. That's good. All right. We're going to do a little bit of 2-4 here. Now, what we're doing in 2-4 is not an A-B topic. If you're planning on, like in engineering, eventually you'll take Calc 3. I promise you'll do this in Calc 3. We're going to do a little tiny toe dip in right now because it's, quite frankly, it's standalone. You don't need anything prior to doing this. We've done everything we needed to be able to use this definition. Okay. Now in a Calc 3 class, the example problems I'm going to give would be considerably more difficult to set up your inequalities for, but like it's still the same idea. So what we're looking at here is, okay, so we go back to this problem here, 59, where it says prove. Prior to this, we didn't really have a definition for our limit that we could use to prove anything, right? We'd like, oh, I looked at the graph and like this, like that's not a proof, right? The only thing that we'd have to be able to prove a limit to this point is the squeeze theorem. What we're going to do in 2-4 is we're going to like give a mathematically rigorous definition for a limit that will allow us then to prove that the limit of something is something. Okay? So that's what we're doing in 2-4. So the definition we're going to use says let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches L, which we write as the limit as x approaches a of f of x equals L, if for every number epsilon greater than 0, there is a number delta greater than 0, such that if 0 is less than the absolute value of x minus a, less than delta, then the absolute value of f of x minus L is less than epsilon. What? So what this is saying is that for every epsilon we pick, we can find some other delta. The epsilon is the gap between the desired limit and some other point on the function. The delta is the gap in the x between what the limit is approaching and some other point on the x-axis. So what we're saying is that somewhere I can find some bounds on the x, or for any bound, any distance between the right answer to the limit and some other point on the y-axis, I can find the 2 points on the x-axis that match up with those y's that contain that limit also. That's what we're saying. So let's look at an example. So this first one says, use a graph to find a number delta such that if the absolute value of x minus 1 is less than delta, then x cubed minus 5x plus 6 minus 2 is less than 0.2. So just to kind of go back and looking at our definition, like this is my a, this is my f of x, this is my L, and that's like my epsilon. So what we're going to do is we're going to try to find that delta that matches up with this specific epsilon. Is everybody okay so far? Yes, Christian.
What's the delta symbol?
That one, it just like looks like that. That's the lowercase Greek letter delta. The uppercase is a triangle. That's one probably you remember from physics or chemistry or something. Talk about delta K's and stuff in there, I think. Okay. So here's where I'm going to start. I'm going to start by changing this absolute value inequality into just a regular inequality. I'm going to get rid of the absolute value. How do I take that inequality and get rid of the absolute value on it? Let's think about it. Let's make the problem simpler for a minute. Let's say I have absolute value of x is less than 2. What range of numbers does x have to be between? 2 and negative 2, right? Everybody agree that those are equivalent statements?
Why does that be greater than negative 2?
Well, because like negative 1, if I take the absolute value of that, that's 1, that's less than 2. Right, but if I pick negative 3, I take the absolute value of that, that's 3, that's not less than 2.
Oh, okay.
Right?
You just take 0.2 and then 0.2 is less than 3.
Yeah. So I just do the same trick that we just did. Everybody's okay there? Okay. Now what I'm going to do is I'm going to get rid of that 2 so that I have just the f of x in there. So I'm going to add 2 to both sides of my inequality. Since my inequality has 2 sides, I have to add it to all the sides. So far, so good? Maybe. Okay. So what I want to do now is I have a range of y values, right? So if we go back to this picture, like this is 2.2 and this is like 1.8. So what I need to do is I need to find what the 3 minus delta and the 3 plus delta should be. Everybody's okay with that? How am I going to do that? How am I going to solve this inequality for, what am I going to use to solve this? It's a cubic polynomial. It's easier than you think. I'm just going to graph it and find an intersection, right? There's not a good way to solve a polynomial in general, right? And if I look at this, there's no hope I have of factoring this thing because it's not like of the polynomial form. There's only 3 terms to it. There's not 4 terms where I could group it. It's 3 terms, but it's not of the polynomial form, like because I have an x cubed, then I have an x to the first. I have nothing I can do with this easily algebraically. I'm just going to do this graphically on my calculator. Yeah, you guys are all like, oh, if you thought that's what you wanted me to do, I could have done that. I should come up with that. Well, sometimes the lazy answer is the good answer, right? And just to be clear, there is no way, even for like a Calc 3 student, that they would have been expected to try to solve this thing without a calculator. So I'm going to go ahead and graph the function. I'm going to graph 1.8 and 2.2. And I'm going to find the intersection. Now, I've done this problem a little bit already, so I'm going to just, sort my window out to a nice place so I can see what's going on. So there's my polynomial. There's my line 1.8, and there's my line 2.2. So I can take this one and this one, or I can take this one and this one. I'm going to take these two, just because. Everybody okay there? Okay. So to find those, I'm just going to do second trace, do the intersect command. So that one and 1.8, and I guess, so I have 1.12. Now, should I be rounding up or down?
Down.
I would do down because this is the upper bound, right?
Oh, is it upper bound?
Yeah, because this x is bigger than this x, right? Because this x is further to the right than the x for this one. This x will be a smaller number because it's left of it. I know it's above it, but that's the y. We're worried about x's right now. So I want to round this down to 1.2 regardless, because if I rounded it up, even you could have something past it, and we don't want that. We want everything to be in between. Everybody's okay? So I have like 1.12. That's going to be the upper bound. And then let's find the other one then. Intersect that one and that one. That should be fine. Okay, 1.91. Should I round this up or down? Up to 1.92. Because if I rounded it down to 9.1, I'd be picking something over here, which is not in between the two values, right? Everybody's...
In between the two values, like,
So if I go back to my picture that we had over here, I want to make sure when I'm rounding my x's, I'm picking points that are still going to land in this section.
okay.
So if I pick 0.91, I rounded down, I'd have an x over here that would correspond to be a point not in that section. Okay? The same reason why the 1.12, we made sure we rounded down because we didn't want to round up and end up with a point over here. And again, like we're outside of where we want to live. Yeah. Does that feel okay? The picture helps, right? Look, going back and referring to the picture about, okay, what am I trying to do? What am I trying to do? What am I trying to do? It helps. Katie.
Wait, why did you choose those?
Oh, you could have used the other two. It wouldn't have been wrong. Everything would have been fine, but those are just the two that I picked because they were, I don't know, furthest to the left. Giselle?
Out of like when you found the intersection for the lower one, how it was like 1.12 and then 1.8, how did you know to pick the x value, not the y value?
So we're looking for the delta, right?
Yeah.
That's on the x-axis.
Oh, okay.
That's what we're trying to find right now. It's like we're trying to build out what this 3 minus delta and 3 plus delta really was.
Got it, okay.
Okay? All right. So now we have this inequality, right? Let me just zoom that back out. So we have this inequality. I want to eventually turn it into that. So what do I need to do? We subtract 1, right? So we can get x minus 1 in the middle. Well, I mean, close. So now we're here, right? So far, so good. So here's the question. So I can do this, or I would do this. Which one would I want? Why the bottom one?
Bottom one matches up. I think the thing's going in the right way.
Wait, so is x minus 1, like, isn't it greater than?
Well, no, if it's between 0.08 or negative 0.08 and 0.12, if I remember the absolute values here now, right? So like this would be numbers between negative 0.08 and positive 0.08. This would be between negative number, right? This is, means this, right? And this one would be this, right? Which one should I pick? No. Why the top one? This one fits, inside of here, right? But this one does not, right? It has stuff too far to the left because negative 0.12 is smaller than 0.08. So there's values of x's that would get us outside of that interval we're looking for. So we want this one. That would tell us delta is 0.08. Okay. All right. Let's do one more. And this is something similar to what you would expect to do in like a Calc 3 class. Now, this is like the easiest possible version of something that you would do here. The stuff you'd probably do would be more difficult than this particular proof, but this is a kind of a standard problem type. So what we want to do, we want to be able to take any epsilon and use that to find a delta. So how do we start with our epsilon? F of x minus L is less than epsilon. Well, our f of x in this case is 4x minus 5, and our L is 7. Everybody's okay there? Okay. If I combine like terms inside of that absolute value, 4x minus 12, less than epsilon. What should the delta look like in this case again? Let's remind ourselves. Should be x minus a less than delta, right? That's what we're looking for. So somehow I want to turn this stuff and try to make it into an x minus 3. So if I factor out a 4, can I bring that outside of an absolute value? Or does it have to stay inside? So you think we have to do this, right? Well, here's the question. If I have two things multiplied inside an absolute value, is this true? No. If you say no, provide me a counterexample. Give me two numbers, an A and a B, where this fails. If you say no, that's fine. It might be no. You might be able to say two numbers. I'm not telling you. I'm asking you to think about it for a moment. If A is negative, okay, like negative 3, and B is positive, say 4, so that would be the absolute value negative 12, which is 12, right? Absolute value of 3, or negative 3 is 3. Absolute value of 4 is 4. So that seems like it's okay with that particular example, right? What do you guys think?
A on the right side was like negative on the outside there.
Well, then it's a different thing. It'd be a different thing if you're saying like there's a negative out here or something.
Oh, then yeah.
Yeah, that's like just a different thing. This is true. This is true. This works all the time. You can break an absolute value out of product, just like we do for a radical, right? When we simplify a radical like the square root of 72, what do? We call that like the square root of 36 and the square root of, times square root of 2, right? And then just make it 6 root 2. It's the same property going on here with the absolute values. So what is that, Mr. Kulik, what the heck is the point of this detour you just took? Is that I can do that. Is everybody okay? Okay. And if we divide both sides by 4, we have that. So what's delta? Epsilon over 4, right? That's all. There's enough in this section for today. Chanel?
Is this going to be on the AP exam?
No. This is just for like personal enrichment. So you've seen it before. Okay. But notice what do we take? 15, 20 minutes to talk about it? That's all we'll talk about it. Just so, in 3 years from now when you're sitting in your Calc 3 class, you'll be like, every epsilon there exists a delta. I don't remember how it goes after that.
I talked to Audrey.
Sure. But that's all we're trying to accomplish here. All right. Let's talk about 2.5 then, and this stuff will certainly be in the AP exam. 2.5. Yeah, this is classic, lots of AP questions related to this topic. So here we're going to be talking about continuity. So remember back to your Algebra 2 or your pre-calc class? How do we define continuity? We said a function was continuous if, like, you could draw the graph without picking up your pencil or something like that, right?
Yeah.
Is that a good mathematical definition? No, right? You can't prove boo diddly with that. So first order of business is to define what we mean by continuous. Now, eventually, we're going to get to like continuous over an interval. But before we can do that, we have to start about just what does continuity at a point mean?
There's a point, like there's a value for x and y.
So what that means is you have to have a point there, and the function has to enter it and leave it. Everybody agree with that? That would be a point. So let's say that this is at the x value, x equals a. So this is like the point a comma f of a, right? So two things need to happen. The limit as x approaches a has to be f of a, right? And f of a has to exist, has to be the point. There has to be a point a comma f of a there. Because we know for a limit, this could be an open circle, and that limit still exists, and it's still f of a, right? So that's what we're saying. To have continuity at a point, the limit as x approaches a has to be f of a. So that implies that f of a exists, it's defined. There's a point a comma f of a. And that the limit exists, and that those two things are equal. Is everybody okay with that? Shana.
So you're pretty much saying that the limit exists if like if it's defined, like
The limit can exist, but it can still fail to be continuous.
oh, okay, got it.
You
Yeah.
need two things. You need the limit to exist, and there needs to be a point where the limit is at.
Like where it's defined, like where like
Let's look at the next example. I think this will help clear things up. Okay? So let's look at this picture here of f of x. That's our graph. What are the discontinuities? Where do we see discontinuities at?
X equals
1. And where else? X equals 3. Good. Anywhere else?
x equals 5.
5 also. Oops. Yeah, come on. Okay. Why is, using our definition of continuity, why is the function discontinuous at 1?
the whole.
Circles will have it.
Okay. F of a is undefined, right? Because there's an open circle at 1, and there's no other point above it or below it, right? So what does that mean? Even though the limit as x approaches 1 of f of x, I guess I should say 1 here instead of, that's equal to, I don't know, whatever that is, maybe 1. But that doesn't equal f of a, which is undefined. Is everybody okay with that? Okay. What's wrong with 3?
There's a hole at 3.
The limit doesn't exist, right?
Oh,
Because the left-hand limit and the right-hand limit are different. Right? The left-hand limit's like -1. The right-hand limit's like 2. And f of 3 is like -1 or whatever, right? Because that's where the filled circle is. What's going on at 5?
And it doesn't equal after
Yeah, so the limit as x approaches 5 of f of x, that looks like it's 1 again. But that's not the same thing as f of 5, which looks like it's, 3 or something. Everybody's okay with what we're seeing? So let's take a look at these 3 functions now. And we're going to determine where we are discontinuous. So let's look at A. What value or values of x is this function discontinuous at? 2. Great, that's correct. Can we show it? That it's discontinuous there? Okay. What's f of, or which one do you want to look at first? Yeah, if we just look at f of 2, we know it's undefined, right? That's enough. If the point's undefined, they can't be continuous there. Everybody's okay with that? Katie, the denominator was 0, so we know that the function is undefined there. Chanel.
Can you go back to like the previous thing? I'm sorry. Why is x equal 5? Like, why is it discontinuous there?
Because the limit is equal to 1, but the point for f of 5 is 3. They're different numbers.
So the limit and the value have to be the exact same?
Yeah.
Okay, so for
Because to think about it, like, would we say this is continuous?
no.
No, right? Because the limit is going to one number, but the function evaluates at another.
Okay, so for x equal 3, is it not only that the limit doesn't exist, but also because, well, the limit, okay, never mind. I get it.
Yeah, the limit not existing is the big problem,
It's
right?
the biggest,
Yeah. Okay. Part B. So here we have a piecewise function, right? What's going on here? Sure, but you probably don't need to. Yeah, at 0. So f of 0 is 1, sure. But what's the limit as x approaches 0 of 1 over x squared? That does not exist, right? We did that in like section 2.2. I think we looked at that same example. Probably go back and find it if you needed me to. There it is. Like positive infinity, right? Either way. You want to call it one or the other. I don't think but we can call it positive infinity if you want. That's okay. Either way, not the same, right? How about C?
X equal 2.
Okay. Why? Nope, the limit exists here. Notice here that we could factor this. So I get 3 for the limit, but f of 2 is 1. Not the same. So if we graph these things, this is what it looked like. The first one, removable discontinuity. Second one, infinite discontinuity. Third one, jump discontinuity, right? If we looked at the picture, so we're almost there in terms of continuity, but we need to be a little bit careful here. So do you guys, if you remember what the square root of x function looks like? Kind of looks like that, right? Everybody agree? Remember that from Algebra 2? If you say so. So does this point meet our definition of continuity?
No.
Why not?
Doesn't, function is better.
What?
The function doesn't enter the points of the limit.
Yeah, so the limit won't exist technically because we don't have a left-hand limit for this, right?
Yeah.
There is no left-hand limit because the function's not coming into anything, just starting. So what do we want to say about that point? Should we call that continuous? I think we would like to. So we're going to clarify, and we're going to add another variation of continuity at a point. We're going to say a function can be continuous from the right or continuous from the left. If the right-hand limit works, we'll call that continuous from the right. If the left-hand limit, I shouldn't say works, if the right-hand limit evaluates to the point, then we say it's continuous from the right. If the left-hand limit evaluates to that same point, it's continuous from the left. Now, why do we, okay, so what, Mr. Kulik? It's because we're trying to get down to talking about continuity of a function over an interval. So we're going to define that as all the points on the interval. The thing we have to be careful about then are the endpoints, right? So we say a function f is continuous on an interval if it's continuous on every number in the interval. Now here's where we clarify. If f is defined only on one side of an endpoint, like in this example, we understand that continuous at the endpoint means to be continuous from the right or continuous from the left or whatever we need. Is everybody okay with that? Okay. All right. So, example. We're going to show that the function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval from -1 to 1. So first thing we're going to do is we're going to check all the stuff in the middle. So I'm just going to take an a from the open interval, -1 to 1. So not including the endpoints, but anything else. If I look at the limit as x approaches a of, let's write it out, this, I can use my limit laws. To do that. And then if I, oops, there's a 1 there. If I do the limit of a constant, that's 1. I can do direct substitution underneath the radical because that's now a polynomial that I'm direct substituting in. I get that. Is everybody okay? Chanel.
Wait, so how come you did like not brackets, you did parentheses for the interval, -1, 1?
Because I have to look at the endpoints separately because I can only look at continuity from the left and right at the endpoints.
Oh.
I need to use a different definition of continuity. So the stuff in the middle, both sides of the function feed into the point, right? But the stuff at the ends, I have to be careful.
Okay.
Okay.
So would you always do this if you're valuing a function?
If it has a bracket,
Yeah.
yes.
Okay.
So if I look at this and I compare it to my f of x, what do you see? Yeah, so what happened? Which is the same thing as you'd get if you did f of a, right?
Yeah.
So there, we have continuity everywhere inside the interval, right? Because I took an arbitrary point and showed that the limit is the same thing as direct substitution. Everybody's okay? If you're not, please say something. We can talk about it some more. I can clarify. Nolan?
So that was just moving everything inside -1
Is continuous. Mhm. Now we need to worry about at those specific values. So at -1, if I'm looking between -1 and 1, I need continuity from the left or the right. Which one? From the right. Because if it's doing this, I need it coming from the right side. Well, when I do that, again, I use my limit laws. Oops. But when I do that, I just get exactly what I need.
So how do you know that this is like good?
Oh, okay. How do I know that I get a check mark here?
Yeah.
Because this limit is equal to what it's evaluating out to. I'm using,
Oh, okay.
it's meeting that definition,
Okay.
right? I just strung everything together in a long equal sign. These are good questions. Don't, like, if you're still not clear, like, stop me,
Okay.
because it matters. Like, if you're not getting what you need to out of it, we can slow down. I can talk more. I can just give you a chance to, like, just give me a minute to think for a second so I can try to get this sorted out. Like, I get it. You're doing this for the first time. It's not easy the first time. That's okay. Okay. One more point to cover, and that's when a is +1. Should I be looking at the limit from the left or the right? From the left. Now, hopefully you can see that, like, this is going to just evaluate out to the same stuff, right? I'm going to skip because it's the exact same work as above. Chanel?
Oh, wait, so how do you know if it's coming from right or left? Like, how do you know if that?
So this is the interval from -1 to 1, right? So, like, let's say this is -1, this is 1. I don't know what this function looks like. Let's say it does like this,
Okay.
just for the sake of argument.
Okay.
So if I'm worried about -1, I have to worry about it coming from the left.
Could you graph this to confirm this, or?
I mean, that's how like functions are going to work. Like,
Okay.
if you go from -1 to 1, the left end you're always going to be taking the right hand limit of.
Yeah.
And the left or the right end you're always going to be taking the left hand limit of. Like, always.
Okay.
So like, I'm drawing the picture to kind of like explain to you how I know,
Okay.
but it's always going to be that way. The left end point needs the right hand limit. The right end point is going to need the left hand limit.
Okay.
Always.
Got it.
Now, let's think about what we've done so far. We defined continuity at a point, right? We've extended that definition now to be able to do continuity on an interval, whether that interval is open or closed, right? Whether it has parentheses or brackets at the ends, right? If it has parentheses, there's no extra step needed. If it's got the bracket at the end, we have to do the extra step of checking the endpoints using left-hand or right-hand continuity. Now comes the good stuff. If f and g are continuous at a and c is a constant, then the following functions are also continuous at a. F plus g, the sum of two continuous functions, is continuous. F minus g, the difference of two continuous functions, is continuous. C times f, the product of a continuous function and a constant, still continuous. F times g, the product of two continuous functions, is continuous. F divided by g, the quotient of two continuous products, is continuous, provided that g of a is not equal to 0, right? This is great, because what I've just done is described a way to take something that's really complicated and determining its continuity and breaking it apart into pieces and just be like, all I have to do is look at the continuity of the pieces. That's good. It gets better. Theorem 5 says a polynomial is continuous everywhere. Everywhere. That is, it's continuous over all real numbers, negative infinity to positive infinity. Polynomials are continuous everywhere. You can use that as a theorem, as a fact, to prove continuity. So if f of x is x squared and g of x is x cubed, f of x plus g of x is continuous because they're both polynomials, and the sum of two polynomials, or sum of two continuous functions, is continuous. Right? I just proved continuity over a new function without having to do any continuity proof from first principles. I just used theorems about polynomials and the sum of continuous functions. Yes, Chanel.
So I have a question on number 5. So what do you mean by g of a is not equal to 0? Like, are you saying at a certain point?
So this is continuity at a point, right?
Okay.
Continuous at a. If you're talking about whether two things are continuous at a, if you divide and the bottom evaluates to 0 at a, that can't be continuous there because you're going to have like some kind of discontinuity.
Okay, so this is like so these are all like rules if they're continuous, like determining if they're continuous at a certain point, not like continuous the whole graph.
Well, here's the thing with a polynomial, they're continuous at all their points, right? So a is everywhere. A is the whole thing, and that's where we want to start getting. We'll keep just. Get there. But that's where we're heading, okay? So yes, we are talking about continuity at a point for these rules. But if you're continuous at all your points, then you just have overall continuity, right? And you can make the same argument. Well, take any point from the reals, it's continuous there, and this one, any point from the reals is continuous there. And if we add them at the same point, any point is going to be continuous at, so the sum is continuous everywhere still. If each of the two were continuous, their sum is going to be continuous, right? Like it's the same idea. But yes, this is specific to a point because of this. That's the one that you have to be worried about. Because you can take two continuous things and divide them and not be continuous at a point if the denominator values to 0 at that point. But that's the only one that can get you in trouble. Okay. Theorem 5, part B says a rational function is continuous wherever it's defined. That is, it's continuous on its domain. So again, you take two rational functions and you add them together. They're going to be continuous over the intersection of their two domains. So the places where f was continuous and g is continuous, you add them together, they're still going to be continuous at those same points. But if f was discontinuous somewhere, but g was continuous, you add them together, it's still got discontinuity at that point, right? So let's look at this example here. It says, find the limit as x approaches -2. Well, what I'm going to do is I'm going to use my limit law. So this is a polynomial, right? Continuous everywhere. Agreed? This is a polynomial, continuous everywhere. Agreed? And I notice that 5 minus 3 times -2 is not 0, right? Everybody agree? So all I need to do now is I can do direct substitution. And what do I get? So if I can show, okay, I muggled this. Let me try this again. I want to attack it from a different standpoint. This is not where that's not the conclusion I wanted to reach. Everything I did was fine. I don't want to be clear. Nothing I wrote was incorrect. I want to lead us to a different conclusion, though. I didn't do a good job of setting up. Okay. Let's look at this. Is this continuous? Everywhere.
Yeah.
Actually, let's be specific. Is it continuous at -2? Yes. Why? Polynomial. Is this continuous at -2? And also non-zero at -2? Yes. So what can I say? Well, it has to equal this. So we can say that if the limit as x approaches a of some f of x is I should say, let me rephrase it. If f of x is continuous at a, then the limit as x approaches a of f of x is equal to f of a. This tells me I can use direct substitution whenever my function is continuous at that point. So remember earlier today where we were like, I was being real careful about like doing my limit laws here instead of just direct substituting?
Yeah.
We can now just direct substitute.
So you can add in.
Now I can use direct substitution much more indiscriminately. I don't have to have necessarily a polynomial or rational thing. All I need is continuity at that point where I'm doing the direct substitution with, which is lovely. Well, how do I know if I have continuity there at a single point? Well, we're going to make it even easier for you now with Theorem 7. The following types of functions are continuous at every number in their domains. Polynomials, rationals, root functions, trigonometric functions, inverse trig functions, exponential functions, logarithmic functions. Basically everything you've seen before is continuous over its domain. Ooh. Now we're talking, Mr. Kulik. So all I have to do is look at the individual functions in their domains and just check to make sure I have continuity at that A in all the different points. And if I do, direct substitute away. All right. Let's get this example and then we'll call it a day. Yes, Chanel.
Wait, so for the previous example, 5 minus 3x, why is it continuous? Is it because it's,
Well, it's a polynomial,
oh, okay,
right?
got it.
It's just a polynomial, and it's non-zero,
Okay.
so we're good. Okay, so let's look at our function f of x. It asks, where is this continuous? Well, when I look at this, I see one logarithmic function, one inverse trig function, one polynomial function.
It's not continuous?
Well, they're all continuous over their domains, but I have to look at each domain separately to figure out the domain for f. So, function domain. Okay. What's the function for the domain for natural log? Should remember this from algebra 2 and or pre-calc. It's a domain, so it's an interval. What kind of numbers can you take the log of? Any is the wrong answer. This domain is restricted.
All real numbers.
Not all real numbers. The domain is restricted.
Rational numbers.
Nope.
Natural numbers.
What? Ooh, well, you can't take the log of 0, but there's a bunch of other stuff you can't take the log of either. Nope.
0.
Non-negatives. Right? Like, what does...
We're so close, guys.
What? Hold on. What's the definition of a log? So it'd be like e to the y is equal to x, right? So what kind of value can come out of e to some power? Can you ever get 0?
No.
No, because the power of some number is never 0. Can you get a negative? The power of a positive is never going to be negative, right? So our domain is 0 to positive infinity.
Good afternoon, everyone. Let's take a moment and stop and pause to reflect on our day.
When they finish, I'd like to finish this problem, though, so don't go running out of here for me, okay?
Something brings in mind where I've seen your presence today. Did I see you working through my friends? Through my teachers? For my family? God, I pray that you work through me to be evidence of your presence to those around me. Amen. Have a great afternoon, Notre Dame, and God bless. Teachers, you may dismiss and you are ready.
Okay, let me finish this up. What's the domain for inverse tangent? Okay, what's the graph of tangent look like? Right? It looks like this, right? Everybody agree? That's what your graph of tangent looks like. The y-coordinates for tangent will be the x-coordinates or domain for inverse tangent. Right? Right?
Yes.
How's that? Okay, now what?
You have to find the domain of x squared minus 1.
Which is?
Is it all real numbers?
Yup. So our domain then is going to be the intersection of these, which is oh, I'm sorry. Here we go. Should be 1 over x squared minus 1. What's the domain of that?
Is it all real numbers except x is not equal to 1?
Or
Or
negative 1. So how do we write that with intervals?
Oh, wait.
that. All right. What's the intersection of all of these now?
150.
Nope.
Negative infinity.
Okay. If you're not sure, if you can't see it, let's graph it. Okay. So I'm going to just graph this all on a number line, and I'm going to look for the intersection. So if I look at the intersection, I have that and that. 0 to 1, and then 1 to positive infinity. You guys can probably do on the homework set up through, let me look here real quick, up through 45. So don't worry about 55A, but up through 45 you should be able to do. Homework quiz next time.
Bye, Mr. Coolidge.
Bye.
Thank you, Mr. Coolidge.
You're welcome.